LeetCode 128, we're given some numbers, and then we have to figure out what's the longest sequence we can build from those numbers where we have got all the integers in that sequence in the order they come in the number line. And we also told to do this in on time. First, I'm not going to worry about that because that makes for a simple solution, and then we'll try to do that to the best of my ability. So we're giving the numbers 100, 4, 200, and then 1, 3, 2. However, I'm going to throw in another element because then we can illustrate a little bit more about what's happening. So the first thing we're going to do is we're going to reorder the elements in the order, and this is where the complexity isn't on anymore. It's probably like n log n for sorting. And we do that using the grade function applied to the argument omega. It gives us the indices that we need of the elements we need to pick in that order that would make them sorted. So if you look at that, this says take element 4, that's this one, take element 6, that would be this one, then 7, so we can see it's a stable sort, and then we go for number 5, number 2, number 1, number 3, and that would sort them. APL has multi-indexing, so we can just do that. And then we can see that the sequence I want to find is the 4-element sequence here, but there are duplicates. So let's remove the duplicates using the unique function. Now we want to do adjacent differences, and that is a pairwise reduction. So it's a reduction over windows of size 2. Problem is that says 1 minus 2, 2 minus 3, and so on. Gives us negative values. We can do reversed windows by saying that the size is negative. Okay, then we want to know if the adjacent difference is 1, because that means they're consecutive, so we can compare all of those with a 1. And we can already see here that we're just looking for the longest group. And we can do this very easily by using the partitioning function. And it takes, if you have a Boolean argument on the left, as you have here, then it just includes the elements corresponding from the right argument corresponding to runs of ones on the left and skips elements on the that correspond to 0 and then begins a new segment. It doesn't actually matter what it is that we are segmenting here because we're only interested in the length of the segments. So we can use the selfie or commute operator to segment that same Boolean data. And that gives us this one list here, and we want to know the length of each list because there could be many of them. We can show that there could be multiple lists. Let's try this. If we say 101 here, so then we get 2 lists. That's for the 101 with the 100. We can get the length of each one, and then we want the largest one, which is the maximum reduction over the lengths of these. And then we're just off by 1 because we are counting how many steps there are, and we want the actual full length of that, so it's going to be a 1. That's what we see. That works. If we add a few more, 102, 103, and then so far it's the same, 104, and now it grew to 5. So it's just one little problem, and that is, while this works fine, we'll not on a scalar, but on a 1-element vector, it is not giving the right result. And also, if we try to give it an empty result, then it doesn't work either because we are trying to do windows of size 2 when there aren't any elements at all. So, how can we fix this? Well, if the length of the argument is 1 or less, then the result is just going to be 1 or 0. That is the length of the argument. So we can make a guard for that. That is kind of like a branch point. So we're saying if 1 is greater than or equal to the length of the argument, then the result should be just the length of the argument. So now we get 0 for this one, and it even works on a scalar, and of course on a one element vector, and as soon as we have multiple elements, then this works as well. So this is a simple solution, but it doesn't live up to the requirements on the time complexity. So for that, we're going to amend this a bit. Now we can only use operations that just traverse all the elements in one go. So for example, we can compute the minimum by traversing all the elements and comparing them as we go along until we find the minimum. That is an ON operation. So let's put in this sample data again. We had 1, 3, 2, and then put another 2 there just for the duplicates. So here we are computing the minimum, and then we can return that and see. So the minimum of this is the smallest element 1. And now let's break out a little bit a subfunction so things don't get so long-winded. What I'm trying to do here is find all the numbers that we have, but we need to do that in the ON fashion. We need to kind of sort them and get rid of the duplicates in an ON fashion. And the way we can do that is by taking the maximum and the minimum, computing the range, and then generate the numbers in that range. It's also ON, and then see which ones we've got. So we're going to define a function n, which are the numbers, and we're going to then apply that on the argument. So we'll see how this goes. We find the maximum, that's 200. And I'm going to now lower these a little bit so that we can easier see what's going on. So now it's 20. Then we're going to have the minimum, which we've defined over here, and we're going to subtract that from the maximum. So this is not minus, this is a commuted minus. So this is the right argument, the maximum, minus the minimum. That should give us the range. So the range is 19. Well, not quite. It's actually 20 because the subtraction is exclusive. But we're going to fix that in a moment. Let's generate that range with the iota, which is the range generator. So we get the numbers from 1 to 19. Then we can prepend a 0 to that. But because this is a monadic function, the way this works is that we need to glue these two together so we get a fork pattern. So applying this function, we're subtracting this value, applying this function, which is just concatenation with 0, where we're pre-processing the right argument with the range generation. Okay, now we've got all the numbers from 0 to 19. These aren't the numbers we actually have. We need to add the minimum value to this. Now we've got the full range of numbers from the smallest one to the biggest one. And now we can use this to filter the argument. So this is a density function applied to the argument. And we're taking the intersection of that and the numbers that we generated over here. And that gives us the same thing. These are the numbers that we have. But if we commute this intersection, that means the main data is this range that we got. Then, since these numbers only occur once, we get rid of the duplicates and we get things into the order that we generated them in. Still only looking up every value once if it's in that array or not, so still ON. Okay, now we're going to take this value, which are our numbers, in order without duplicates, and then we're going to continue without generating these partitions, because that's going to be costly. Instead, we are going to start off with doing the adjacent differences. And then we're looking at where are these different from 1. Now we can we have this result here, and we want to find out what are the starting points and the ending points of sequences, which actually starting point of sequences of runs where we have consecutive integers, so that we can find out how long they are. And we do this by putting a 1 on the left and putting a 1 on the right, so there's a concatenation with commuted arguments. And now we can see we got a longer result. So here are our 1, our 2, our 3, and our 4. And these are the, should we say, the cutoff points, the boundaries of that. And then we have the 100 lives here and the 200 lives here. These are the boundaries between the runs. Each run is only 1 element long, so it's 1 space here long. Then we can get the indices of these ones. And this tells us we had a 1 over here at positions 1, 5, 6, and 7. That's 1, 5, 6, and 7 over there. And now we have the indices, then we can subtract them from each other in the same way as we did before, with a pairwise reduction over windows of size 2. And that gives us the length of all these runs, and all we need to do now is take the maximum of that, which again is just the ON operation. This is an ON operation, which is converting these booleans to values, and the pairwise, again, just by the number of them. It's going to be less even than ON, depending on our value, and this, of course, is, again, ON on this already lessened value, so that doesn't matter. And that gives us our maximum length. And this solution still has the issues with if we give it a 1 element, that is fine. But if we give it a 0 element, so empty numeric vector, then it's being handled over here as well, and that is a good solution.